Welcome to this video on what is radiation. Okay, I'm going to split radiation into two parts, but let's look at the textbook definition, a definition I found on the internet. The emission of energy as electromagnetic waves or as moving subatomic particles, especially high energy particles which cause ionization. That might make sense to you, it might not. Either way, I'm going to try and sort of simplify it a little bit. So as I said, I'm going to split it into two. I'm going to split it into electromagnetic radiation. Now, electromagnetic radiation, this is an energy transfer in the form of waves like microwaves or infrared, visible light, and so on. I'm not going to spend any more time on this because I've made a video on it. All you need to do is click on the link above and you can find out lots more about electromagnetic radiation. The other type is nuclear radiation. So called because it comes from the nucleus of the atom. Now at this point, if you haven't studied the structure of an atom, stop this video, click on this link and watch the video called How to Draw an Atom. If you don't know your way around an atom, then some of this stuff might not make sense. If you do, if you know about atoms and protons and neutrons and electrons and how they're all arranged in an atom, then we can go ahead now and talk about alpha, beta and gamma radiation. So starting with alpha. In alpha radiation, you have an unstable nucleus, and this unstable nucleus fires off a lump, and this lump is made of 2 protons and 2 neutrons, so it has a mass of 4. And that is exactly the same as the nucleus of a helium atom, hence the He next to the alpha particle. Now this alpha particle flies through the air, collides with other atoms, causing ionization, and we'll talk a little bit later on about what ionization is. Now look at the daughter nucleus. The total mass has changed. What's happened? It's gone from 238 down to 234. So the relative atomic mass has gone down by 4 because it's lost 4 bits. The proton number has gone down by 2 because it's lost 2 protons. So it's changed from uranium to thorium. And that's what happens when you get alpha decay. By atomic terms, alpha particles are big. They're a big lump, like a cannonball. It's highly ionizing, highly damaging, but it's not very penetrating. It wouldn't go through a piece of paper. So if you wanted to hurt someone with an alpha source, you'd have to either feed it to them or inject it into them. So it's really not very penetrating at all. Now, before I give you an example of how alpha radiation is used, I want to explain ionization to you. So you get this high energy radiation, like this alpha particle, flying through the air. It smashes into an atom, like, I don't know, like something in the air, nitrogen, oxygen, and it knocks an electron off. And if it knocks an electron off, if you remember, electrons are negatively charged. So if you lose an electron, you're going to become positive. You become a positive ion. We don't call it an atom anymore. It's now an ion. So the radiation smashes into a molecule or an atom, knocks an electron off or 2, and we have a positive ion formed. It could knock a proton off, and if it did that, you've lost a positive. And if an atom loses a positive, it's going to become a negative ion. So have a look at the magnesium atom in the corner of this slide. It loses 2 electrons in its outer shell, and therefore it becomes a 2+ ion. So here we are. Let's look at one use of alpha radiation. It's being used here in a smoke alarm. We've got a positively charged plate at the top and a negatively charged plate at the bottom. And we've got ionization events going on. The alpha particles are flying through the air, smashing into the molecules, knocking electrons off and leaving positive ions. So we've got positive and negative ions in this gap between the positive and negative plate. Opposites attract, so the negatives will move up to the positive charged plate and the positives will move down to the negative charged plate. And the effect this has is to keep the current flowing and flowing and flowing. Now, let's say you get smoke in between these 2 charged plates. What's going to happen? Well, smoke is enough to block the alpha particles. It doesn't take very much. If they block the alpha particles, there's no ionization because they're not colliding with the air particles, the air molecules. No electrons formed, no ions formed, and therefore the current stops. And if the current stops, the alarm goes off. It's quite possible as well that the individual little smoke particles are absorbing the ions. If there are any ionization events, those electrons and positively charged ions are actually joining with the smoke particles, so they're not getting to the charged plates. Either way, the current stops. The flowing current stops, and that sends a signal to sound the alarm. So you want a current, a continuous current, and you're going to use an alpha source for this. In beta decay, a neutron in the nucleus turns into a proton and an electron. Okay, a neutron actually physically turns into a proton and an electron. The proton stays where it is, stays in the nucleus, and the electron is fired out of the atom. So the mass number stays the same. A neutron weighing 1 has turned into a proton, which also weighs 1, so no change in the mass number. But the bottom number, the proton number, that has to go up by 1 because we've gained an extra proton. So that's beta radiation. Beta particle. A beta particle is fairly penetrating, moderately penetrating, and moderately ionizing as well. So let's talk about one of the uses of beta radiation. In the manufacture of aluminium foil, or aluminum foil if you're in the States, is a good example of a use of beta radiation. A radioactive source is placed above the foil and a detector below it, and if too much of this beta radiation is reaching the detector, that means the foil is too thin. So it sends a signal off to the rollers to reduce the pressure, don't squeeze so hard, and that causes the foil to get thicker. Now, if too little radiation is being detected, there's not enough radiation coming through, that means that the foil must be getting thick, and you send a message to the rollers to apply more pressure, and the foil gets thinner. So the foil stays within a certain boundary, at a certain sort of thickness throughout, and that's one use of beta radiation. Finally, gamma radiation. This is a high-frequency electromagnetic wave. There are no protons, neutrons, or electrons involved. It's just a wave. So the mass and the proton number both stay the same. Having said that, there is still enough energy in a gamma ray to cause an ionization. Okay, so then in gamma radiation, the numbers don't change one bit, but it's still ionizing, it's still damaging. If you know, when a nuclear bomb gets dropped, if you don't die in the blast, then and if you're anywhere near it, you may well be irradiated. You may well have some genetic mutations caused by gamma radiation from a nuclear blast or something like that. Gamma is the most penetrating of them all. It takes thick lead or thick concrete to stop it. However, it is the least ionizing of the nuclear radiations. Compared to other EM waves, compared to infrared and the other waves, it is very ionizing, but as I say, not compared to alpha, beta, and gamma. It's the least ionizing of the three. One use of gamma radiation is in sterilization, so we can sterilize surgical equipment or even our own food. With a blast of gamma rays, we know that there'll be no bacteria or fungus causing a decay and causing all that nasty food spoilage, so we can use it for sterilization. Okay, there we are, a very quick run through of the different types of radiation: alpha, beta, and gamma, nuclear radiation, and EM radiation as well. I hope that was useful to you. Have a go at these questions. Pause the video now, write some answers down, and I will change the slide and the answers will flash up in a second. If you know someone else who's going to benefit from a video like this, then hit the share button, and thank you very much for watching.
Ionizing radiation, which is energy that's given off by radioactive materials. Ionizing radiation has a lot of energy, much more than the low energy radiation from radio waves, cell phones, and microwaves. These types of low energy radiation are called non-ionizing radiation. Ionizing radiation has potential for interacting with and changing atoms and molecules. This is an important distinction which many people may not realize. For simplicity, we'll just refer to it as radiation. If radiation hits the cells in the body, it can damage or even kill the cells. The amount of energy that the body absorbs from this radiation is called the radiation dose. At high doses, and when most of the body is exposed, enough cells die to impair the function of various organs in the body, and that can lead to really serious health effects, including death. If only a specific part of the body is exposed and the dose is high enough, it could lead to localized effects, such as skin injury. At low doses, if any cells are damaged, the cells may repair that damage with no consequence, or the cells may leave the damage unrepaired or repair it incorrectly. And these may have long-term consequences and could potentially increase risk of cancer.
You used the word exposed. Is this term used differently for radiation hazards than other environmental hazards?
It is. When our bodies absorb the energy from radiation, we're being exposed to radiation. We don't have to come in contact necessarily with any radioactive materials. If we walk away from the source of radiation, the exposure stops.
So like with an X-ray, you're exposed while the X-ray is being taken, but you don't take any of the radiation home with you.
Exactly. Now, in contrast, if radioactive material gets on our clothing, skin, or hair, it contaminates us. We call this external contamination because it's on the outside of our bodies. External contamination can be removed simply by taking off contaminated clothing and washing with soap and water. If we inhale or ingest radioactive material, we call that internal contamination because it's now inside our bodies. It's harder to remove internal contamination. Our bodies can get rid of some of it through metabolism and excretion. And for some types of radioactive material, we have medicines. We call them countermeasures that can speed up the
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Radiation exposure. X-rays ionize human tissue and deposit energy that can cause harmful changes within the body. There is a cancer risk from X-rays. The dose of radiation is cumulative. X-rays are considered for carcinogen list. The government is attempting to avoid the use of unnecessary CT scans and X-rays to avoid unnecessary exposure to radiation. This highlights the cancer risk. Doctors need to pay close attention to the risk involved with the use of X-rays. The cancer risk associated with radiation exposure is documented in cases of atomic bomb survivors. The risk for medical uses is controversial and usually played down by physicians. Radiation at a high level is carcinogenic. The level of radiation from X-ray exposure is low. The effects of low-level radiation is not known. So what is the safe radiation level? The safe level is not known. It is known that CT scans, fluoroscopy, mammography, and X-rays expose the public to a high level of radiation, especially in young females. The risk of exposure should balance the medical benefits. Optimize radiation doses by exposing the patient only to enough radiation to get a clear image. There is a growing concern about the risk associated with giving a patient large doses of radiation. The use of CT scans has increased recently in adults and children, possibly exposing the patient to an unnecessary high dose of radiation. CT scan is the method most often used to diagnose cancer, diseases, fractures, and it exposes the patient to a much larger dose of radiation than X-rays. Radiation from CT scan of the pelvis equals the same amount as 100 chest X-rays. Children are 10 times more sensitive to radiation than adults. 3 to 4 million children receive CT scans and about 1,500 of them will develop cancer 2 decades later. Children should not be given an adult dose of radiation. Radiation dose limits. CT scan of the pelvis has the highest level of exposure to the skin, marrow, and gonads. Use a mini fluoroscopy C-arm whenever possible. Radiation exposure with fluoroscopy. Fluoroscopy emits a lot of radiation. The closer the extremity is to the radiation source, the higher the dose of radiation the patient receives. When the distance from the beam increases, the dose of radiation is less. Radiation intensity follows the inverse square law. It is all about distance. If the intensity of radiation at 1 meter from the source is 100 milliroentgen per hour, then the intensity of radiation at 2 meters from the source is 1/4, or 25 milliroentgen per hour in same unit area. At 3 meters from the source, the intensity of radiation is 1/9 the original, or 11.1 milliroentgen per hour. There is less exposure to the physician when imaging a smaller body part. Larger body parts create an increased exposure to the physician when imaging a patient with the C-arm. Do not be in the direct path of the radiation beam. Radiation protection is of importance with monitoring, shielding, and position. Monitoring protection should be used with a dosimeter badge. A dosimeter badge only records how much radiation you have received. It does not protect you from exposure to radiation. Shielding protection of fluoroscopy radiation. Lead gowns and aprons work to stop exposure. Lead aprons attenuate scattered radiation by about 95%. Rapidly dividing cells are most sensitive to radiation exposure, such as sperm, lymphocytes, the small intestines, and stomach. Radiation damage seldom appears at the time of irradiation. The first effects of radiation damage is usually seen as a drop in the white blood cell count. The first external sign of damage is seen as a skin burn. Studies suggest that people who use fluoroscopy extensively have a higher rate of cataracts. Early effects of radiation exposure could include death, hematologic depression, chromosome aberration, skin erythema, or epilation. Here are some facts about team exposure to radiation. CT scan examination is usually done without justification by most insurances. It is opinion that 1/3 of CT scan studies that are given could be avoided. Giving unnecessary studies causes an added cancer risk with no benefit. The CT scan study should be justified. There is no close oversight or uniform standard in order to eliminate radiation exposure. This must be done. Patient education is important. The patient should ask if the study is necessary and what is the lowest dose possible that can be given without compromising the study. There should be a universal X-ray bank where patients' X-rays can be accessible anywhere from any hospital. This would avoid the unnecessary repeating of X-rays.
Wi-Fi is a convenient way to connect to the internet, sometimes for free, regardless of where you are. But it's not without a cost. You see, Wi-Fi is a form of electromagnetic frequency radiation, also known as EMFs, which are generated by all electronic devices. Wi-Fi specifically is a radio frequency form of EMF. Wi-Fi routers use radio transceivers to connect to the internet on either a 2.4 GHz or 5.8 GHz radio frequency band, depending on range and speed. Wi-Fi signals can travel hundreds of feet, and within a room, whether it be a coffee shop, house, airport, or school, these high-density transmissions multiply as more people connect. Studies show this exposure can lead to many health issues, such as infertility, DNA fragmentation, neurological damage, and even cancerous tumors. Kids are even more susceptible to EMF radiation, and early exposure has been linked to behavioral problems like ADHD, memory and cognitive impairment, and an increased risk of obesity, asthma, and depression. While there are many benefits of technology in schools, there may be hidden health risks. It's impossible to avoid all Wi-Fi, but you can reduce exposure by turning off routers when not in use or by connecting to the internet using an Ethernet cable. Nowadays, we're spending a lot of time connected to mobile devices like laptops, tablets, and cell phones. The problem? All these devices emit a form of energy called electromagnetic field radiation, or EMF radiation for short. When we constantly use our mobile devices close to our bodies for long periods of time, our exposure to EMF radiation can become harmful. Research has shown correlations between EMF radiation exposure to everything from minor concerns like headaches and skin rashes to more serious concerns like fertility problems, cell damage, DNA fragmentation, and even cancerous tumors. So how do we protect ourselves? Of course, the best and most effective form of protection is abstinence. Don't think about technology, don't use it, don't touch it, don't even dream about it. Getting rid of EMF sources will get rid of your exposure to EMF. But abstaining from electronic devices is really, really hard.
Let's get real. I know asking high school seniors to be abstinent is like asking a porcupine to poop goat cheese.
If you gotta have them, you gotta have them. So the next best option is to decrease the amount of time you spend on them. Don't just scroll through your Instagram feed for hours or listen to your Bluetooth music all day just for fun. Use your devices less and you'll expose yourself to less radiation. When you're not using them, turn them off, or at least put them in airplane mode. Can't seem to disconnect? Then keep them as far away as possible.
Far away.
Radiation is exponentially stronger the closer you are to it. That's because it follows the inverse square law, so try to keep at least a small distance between you and your device.
All right, I get it.
Having it just 1 foot away will decrease exposure by 80%. While sleeping, keep your phone at least 4 feet away, and keep your Wi-Fi router at least 10 feet away at all times.
Put that thing back where it came from, also help me. Get that thing away from me, you guys.
So your job, or maybe just your social lifestyle, needs you to be right next to your device with it on and connected 24/7. What can you do? First, wire up. Radio frequencies are created by a wireless connection. To eliminate these radio frequencies, use a wired keyboard, mouse, headphones, and an Ethernet cable, instead of Wi-Fi and Bluetooth options. To complete your EMF protection toolkit, use a radiation shield for your mobile devices to block EMF radiation from reaching your body.
Get this man a shield.
Shielding technology blocks EMF radiation from all sorts of devices. Just do your research on EMF shields to make sure they're scientifically tested. If you're concerned about the health effects of EMF radiation from mobile devices, just remember, reduce the sources around you, spend less time on them, keep them away from you, use wired accessories, or get a radiation shield to reduce your exposure to EMF radiation.